Hello, everyone. Welcome back to Grade 10 Academic Math. This is our lesson 16. We're going to talk about the sine law and cosine law. Okay, so this is actually the last lesson in the course, the last video lesson in the course. There's one more lesson, lesson 17, but it's a sort of do-it-yourself lesson. So this is the last video that you'll be watching for this course. Congratulations. So sine law and cosine law. This is extension of trigonometry. So what have we seen so far in trigonometry? Basically, we came up with these three equations, these three what we call primary trigonometric ratios of sine, cosine, and tangent. Okay? And it was able to relate the proportional lengths of sides in a right angle triangle. So if we have a right angle triangle and if we have an angle, our angle here is theta, it's unknown, or maybe could be known. Just this is the one that we're using to label, right? From that angle theta, we were able to label an opposite, the farthest away side, the closest side, the adjacent, and the hypotenuse, which is the longest side of the triangle. And we were able we generated these proportions, like opposite divided by hypotenuse. So the length of the opposite side divided by the length of the hypotenuse is equal to a ratio which we called the sine of the angle. And using similar triangles, we're able to show that we can make it bigger or smaller, and it won't change this ratio. So we have these three, and we were able to solve problems with our trigonometric ratios. Now, the problem is, what happens if we get to a situation where we don't have a right angle triangle? Let's say, like for example, here everything is all related to right angles. But what happens if the triangle looks like this? So as you can see, there's no right angle triangle here, so we can't use our primary trig ratios. Okay, make sure if you see a triangle without a right angle triangle, please do not use the sine, cos, and tan as they are. Okay, we can't. It doesn't work like that. However, we can construct two right angle triangles from this picture. Right? I can first label our opposite sides. Right, so this is angle A. So that means that the side farthest away from it, we can label side A. This is angle B, so this becomes side B. Angle C, lowercase c. So notice the capital letters represent the angles, and the lowercase letters denote sides. Always keep that in mind. If you see a capital letter, it means it's an angle measured in degrees. And if you see a side, it's a length measured in whatever units they give us. So from here, I can construct an altitude. Remember, this is a line at right angles to one of the sides up to another vertex. So as I just said, it creates a right angle triangle, right? This angle here, these are two right angles. So we have two right angle triangles constructed out of our triangle ABC. So we have ACD as a right angle triangle and BCD as a right angle triangle. Okay, so now that I have right angle triangles, I can actually use my primary trig ratios. So let's think about how we can do that. So this angle A over here, I can label side H as the opposite of that angle. And if I divide it by B, the hypotenuse, I have the sine ratio. So the sine of the angle A is equal to H, this altitude that I constructed that's opposite of A, and divide that by B, the hypotenuse of that triangle I created. And solving for H, I end up with B times sine A. And the reason I'm solving for H is because I can do this again with the other side, other triangle here. This is angle B, capital B. The sine of that angle will be opposite over hypotenuse, or H over A. Now that I've got two equations that both equal H, I can do a little substitution. I have two equations, two unknowns. It's basically a linear system of equations. I end up with B sine A is going to be equal to A sine B, because H has to be equal. This H, this height of the triangle, that has to be the same since I constructed it out of triangle ABC. And now I can actually cross multiply, and I come up with this nice equation, this nice proportionality statement, that the sine of an angle divided by the length of the opposite side is equal to the sine of another angle divided by its opposite side. And this is actually what we call the sine law. There is a proportionality between the sines of the angles and the length of their opposite sides for all A, B, and C. Okay, so this is another proportionality statement about triangles that we can have. We had one for the side lengths, and then we had one for the areas, and then we can also come up with one about the sine of the angles. And this is a very powerful equation that we can actually use. Now, notice that the fractions relate always opposite sides and angles. So that's the main thing that you have to remember when we do these things. So let's try an example to see how this works. Oh, before I move on, sometimes in textbooks, they actually write it upside down. So they take each fraction and flip them over. That's okay, right? I can flip a fraction entirely. And it doesn't really matter. I just like it written this way just because it's the sine law, so it's the first thing you write in the equation. It's just, I don't know, that's how my brain works, so that's how I write it. So let's try an example here. So let's say I have this triangle ABC. I know two of the angles, which actually means I can calculate the third one, but don't worry about that for now. So I have 98 over here, 62, and I have 18, which notice is opposite of angle C. So 18 is actually lowercase c. So when I do these problems, the way I like to do them is I just draw a circle around the opposite pairs. Right? We're caring about finding out a proportionality that has these opposite pairs in them, right? So I can take these opposites and I can put them into my equation. Notice I'll have one unknown here. X is my unknown side length. However, I have the other pairs. And what do I mean by that? Okay, so I have A, sine A over A is equal to sine C over C. Now these letters, that really doesn't matter. I just, you could, as long as it's the same letter pair in your equation, it doesn't matter what letters you use. I could have labeled these D, E, F, X, Y, Z. It doesn't matter as long as in our equation we put the same pair. Okay, so sine of A is 98, X is A, and then our other pair is 62, or sine of 62 divided by 18. And here you can see I have a nice little proportionality, and I can solve this quite simply by cross multiplying. So X is going to be equal to multiply across the diagonal and divide by the third side. Oh, that's always the trick. If ever you have any sort of proportionality statement like this with an unknown, we have a known diagonal. So sine 98 and 18, these are known quantities, right? Sine 98 is just a number, 0 point something or other, 0.9 something. So whenever we want to solve this, we multiply across our diagonal and then divide by our third side. So we come up with the equation 18 times sine 98 divided by sine 62. Plug that in our calculator carefully. Okay, the place you're going to make mistakes in these problems. There's two places you're going to make mistakes. You're going to substitute in incorrectly. Okay, make sure these are always opposites. That's why I did the circles. Make sure you do the opposites. And the other thing is when we do this calculation, we might plug it into our calculator wrong. So just be very careful. And remember, always check that you're in degrees, not radians. Okay. And then when we just solve that in our calculator, we get 20.8. Now, another thing you should do when you do these problems is look at your answer and think, does that make sense? Is my sine x, this length here x, does it make sense for it to be 20.2? And look at here, I got 18 here, right? So is this side length, is it longer than 18? Yeah, so it's okay. I like it. We're good. Okay, so if you got a number that was less than 18, you know you did something wrong. Maybe you did the wrong substitution and you got this side instead or something. Okay, so just take your time in substituting and figuring out which one you got. Okay, let's try another one. Okay, so what happens now if we have, let's see, I have angle A is 65 degrees, angle C is 75 degrees. I have side X that I'm looking for, and I know that A, lowercase a here, is 34. So I have a pair. Right away, I can see that I have a pair. Now, the problem is I don't have angle B. Right? I don't have this pair. I don't have enough. I don't have the information here. I don't know. Like for me to use in my formula sine of B divided by X, let's say, I need to know what that angle is, right? I have here sine of C, but I don't care about side length C. So I need to somehow figure out B. And it's actually pretty straightforward because we know that a triangle, all the angles, are going to add up to 180. And I can figure out quite quite easily, that angle B is just 40 degrees since it's 180. Take away the two knowns, 65 and 75. So now that I have angle B, I know 40, and have this pair now, 40 and X, and I have the other pair, 65 and 34. I can plug those into my sine law formula, right? So sine of 65 divided by its opposite, 34, is equal to sine of 40 divided by its opposite, X. And then X is just going to be, again, we multiply across the diagonal, 34 times sine 40, and then divide by the third side, sine 65. Sorry, by the third piece of information in our proportionality statement. All right, so we get 34 sine 40 divided by sine 65, plugging this into our calculator, and we get 24. Now, does that make sense? Let's look again. Can this side be 24.1 if this is 34? Yeah, that looks pretty close. Okay, it's not larger than 34. I think I drew that when this isn't to scale, right? It's a 40. This angle should be a lot smaller in the picture. Anywho, all right, let's try another one. Slightly different here. Unknown angle. So this, in the last two examples, we were looking for unknown sides. Can we do the same thing for an unknown angle? So let's look here. I have a pair of known angles and sides, opposite angles and sides, and I have another pair. So we're good to go, right? We know sine of theta over 12 is going to be sine of 47 over 10 using our sine law, right? So we have our known pair, sine 47, divided by the opposite, 10, is going to be equal to sine of theta. Careful, you don't forget this sign here. Sine of theta divided by 12. And again, I have an unknown. There is this little caveat that there's a sign stuck to it, but this is my unknown piece. So I can get that. I can isolate that unknown by multiplying across the diagonal and then dividing by the third side. So it's going to be 12 times 40 sine 47 divided by 10 is going to be equal to sine of theta. Now, that's not equal to theta. That's going to give us a number like 0.878. Okay, that'll give us a number. So this is telling us the sine of some angle theta, some unknown theta, is going to equal 0.878. The question is, what angle does that? So to get that, all we have to do is we take the inverse sine of our number. Second function on your calculator, or inverse, however your calculator works. We undo what the sine does. And that'll give us an angle of 61.4 degrees. Okay, so if we're looking for an unknown angle, it's the exact same method. The only thing you do is at the very end, we have to take the inverse sine of our answer. Right? We end up with this expression. Instead of just x equals something, we get sine of theta equals something. And then we have to do the inverse sine to get our final answer. And again, we should just look at our picture. Does that make sense that this is 60? Yeah, we're good. Okay, so one more example here. So let's look for some pairs here. What do we got? We got x sine 62 Uh-oh, we got A in 67, and we got B in 42. Uh-oh. If I plug this into my formula, I have nowhere in here. I've a bunch of ones. I got an unknown here, right? Unknown A, unknown B, and unknown C. None of these fractions I can use to solve any of them. I don't have enough information. There's a hole in our problem. We can't solve that equation. There's not enough for us to go on. If I only worry about the first two terms, I have A and B unknown. Okay, that's not going to work. If I just use the last one, I got B and C. That's not going to work. If I use the first and the last, I got A and C. There's no way that I can come up with an equation that I can solve to get this. So we need another tool in our trigonometric toolbox to let us to solve this. So let's start again with our triangle. This is now cosine law. Little spoiler alert there. So let's start again with our general triangle ABC. And again, we can label it ABC, lowercase ABC. And again, we can come up with an altitude, making this into two right angles. However, instead of trying to use sine to solve things, let's go back to grade 9. Let's go back to Pythagorean theorem. If I know that the side AB, has a length of C, then I can come up with two triangles where I know all three sides, right? I know H, B, and X. This is some distance X. And another one where we have a length C, the larger one, subtract, it's the difference between C and X. It's going to be that piece there. So let's use Pythagorean theorem. For the left-hand triangle, we know that b squared, the hypotenuse, right, b squared, is going to be equal to x squared plus h squared. That's just Pythagorean theorem. And again, I'm going to solve this for h. I'm going to get h by itself, so I'm going to bring the x squared over. It's going to become negative x squared. And we can do the same thing for the right-hand triangle. A squared is equal to c minus x all squared plus h squared. And again, solving for h, we're going to take this whole bracket, x minus c all squared. We're going to take that all over to the other side. And I now have two expressions for h squared. And we can do the same trick. We can set them equal to each other. So I end up with b squared minus x squared. That's this one here. And a squared minus x minus c all squared. And that's that piece there. Right? We've been able to get rid of our h, just like we did for sine law, where we set them equal to each other. But in here, we're setting h squared equal to h squared. Okay? Now, you should notice here, this is c minus x all squared. I can FOIL this out. I can expand this. Right? This is c minus x multiplied by c minus x, and then I can do our first outside, inside, last. And I can come up with c squared minus minus 2xc, so that's going to be 2xc plus x squared, because that's going to be, right, this is just, if you're confused about that, we're just foiling that out. That's going to be c minus x, so it's going to be c times c, which is c squared, negative xc, so that's 2 negative xc's, and then negative x times negative x is positive x squared. I'm subtracting all that, so I can rewrite it. So this is going to be negative c plus negative, right? I'm just changing the sign of everything on the inside bracket. Now you can see I have x squared and x squared. They can cancel out since they're on both sides of the equation. And I can come up with the expression that b squared, so this length squared, is equal to a squared plus 2 times xc. Now we still have x in here. This is sort of annoying that there's this x here that's related to the two triangles. There's some way that we can get rid of that. That'd be nice. So the way we can look at that is, let's again consider triangle, this left-hand triangle. this is D. Let's consider triangle ACD. And we know that the cosine of A is going to be equal to x. Uh-oh, I made a mistake here. That should be x. Oopsies, that should be x as well. The cosine is going to be the adjacent side, which is x, divided by the hypotenuse, which is b. So x is just b cosine of A. Right? The length of x is going to be equal to the hypotenuse of the triangle B times the cosine of the angle. So I have this expression x equals b cos A, so I can replace that in my equation. Okay, and solving for a squared, getting a squared all by itself, I end up with this wonderful equation, which is actually just what we call the cosine law. It looks very similar to Pythagorean theorem. Pythagorean theorem, actually, you can think of it as a specific case of the cosine law. Because in Pythagorean theorem, it's a 90-degree angle, and the cosine of 90 is 0, so this whole other term disappears, and we just end up with Pythagorean theorem. Now, it does look a little bit tricky because it's a on this side and not c squared equals a squared plus b squared, but that doesn't really matter. You could have written this in any order of a, b, and c. I just did it in this fashion, so we got A, B, C, so it looked nice. But it really doesn't matter what the letters are. As long as whatever letter you have in the front by itself, so in this case I have a squared is equal to, so in the front at the beginning it's just a squared. The angle in the cosine has to be the same letter, well, the capital of that letter. So a at the front, a at the end. And then the other letters on the inside just have to be the other two. So I could have written this, what I mean by that is I could have written as b squared is equal to, and it's going to be cosine of b, and then the other letters are just going to be a squared plus c squared, and then subtract 2ac. That's also true. This expression is also true. That's another version of cosine law. Or you could even go c squared is equal to, it's going to be cosine of c, and then the other two letters. So that's going to be, what are the other two letters? If I have c, I'm left with a squared, b squared minus 2ab. That's the one I actually prefer the most because it looks the most like Pythagorean theorem. It really doesn't matter what the letters are, as long as the first letter and the last letter match, and then the other letters on the inside are the two others. Okay, so that's cosine law. And we use this, the time we use this, the time that we get stuck, always use sine law. Okay, sine law is so much easier. There's so many less, like here we got squares, we got multiplying, we got a negative. There's a lot more operations involved. So always use cosine law because you're less likely to make any little silly mistakes. We use the cosine law. Sorry, I just realized I was floating in space. We use the cosine law whenever we have what we call a contained angle. Oops, a contained angle. And what do I mean by that? Let's say I have A as my known angle. Let's say, well, I don't know what that would be like. I don't know, 50 degrees or something like that. And then I know side length B, and I know side length C. So when I have all my knowns, let's say this angle here, this known angle 50 is contained within, and let's say this is, I don't know, 16 and this is 18 or something like that. If I know my known sides are around my known angle, it's contained within it. This angle is contained within known sides. I have to use the cosine law. Because in that case, sine law won't work because there's no what's it called? There's no pair of these things that I can actually solve the problem with. Okay, so let's see what I mean by that. So here I have an angle 62, C, and then I know length B, and I know length A, and that's containing angle C. I don't know side length C. Okay, so how do I solve this? Let's write out the cosine law with C, because that's my unknown, right? So C squared is going to be equal to A squared plus B squared. Look at that, Pythagorean theorem. Weird, eh? But, and then cos of 90 is 0, but whatever. Don't worry about that. So you can think of cosine law as just like a modified version of Pythagorean theorem, what we used in grade 9. Okay, it's just we're using this extra 2ab cos C to modify it for non-right angle triangles. Okay, so I can substitute in what I know. Now this is where you're going to make some mistakes. This is first spot that we're going to make mistakes. So we got to be careful. Okay, so my unknown is here x. So that goes into the left-hand side by itself. Then my two sides are 42 and 67. So I'm going to put those in as a and b. And that's also here, subtract 2 times 67 times 42 times the cosine of the angle opposite my unknown. So my unknown is here, x. The angle opposite that is 62. The cosine is 62. Okay, so be very careful when you're doing this, that we substitute in appropriately. Okay, that's the first big mistake you can make, that we put the things in the wrong spot. Now, the other mistake is evaluating this. Be careful that, remember, this we have to follow BEDMAS. So this cos of 62 is just a number. So really, we got to be careful that we multiply these four numbers. There's four numbers here: 2, 67, 42, and cos 62 is just a number. So you multiply that first, and then subtract it from it. Okay. So when you plug it, it's a good idea to do all that first. So we square 67, square 42, and then multiply all these numbers together. Okay, and then write that as a subtraction. Now, another problem here. If my angle is greater than 90, the cosine of anything between 90 and 180 is actually a negative. So if my angle is greater than 90, I'm going to have a negative number here. So a negative times a negative actually becomes a positive. So the sign right here, you can make a mistake there. Okay, that's another common mistake to be careful of. If our angle is less than 90, we're going to subtract. If it's greater than 90, we're going to add. So just be careful there. So again, this is why I'm saying use sine law most of the time, because there's a lot of places you can make mistakes here. Right? Even if you know how to use cosine law, you can still easily make some mistakes in the evaluation. All right, so we got three things to add or subtract. So that works out to 3,610.8. But that's the side length x squared. So we take the square root of both sides and we get 60. Okay, so this side here is 60. And again, we look, does that make sense? This is 42, this is 67. Yeah, that makes sense. It's between the two, right? We can see that AB is smaller than the BC, but it's also bigger than AC. So that makes sense. Okay, so just take a quick second, look, make sure your answer makes sense. All right, so that's how we use the cosine law. Basically, Pythagorean theorem with a correction term on the end of it. Let's try another one. Now we can see another use for cosine law is if we have all three sides of a triangle that's not a right angle triangle, and we want to find out one of the angles. Okay, if we have all three sides of a triangle, we can figure out the angle using cosine law. So again, let's write down our cosine law. And we want to find the angle. We want angle C. So I wrote it in terms of C, A, and B. So I put C on the front and the end, right? These have to match. The first letter and the last letter have to be the same. So how am I going to solve this? Let's do a little bit of rearranging. Let's get the angle by itself. So let's subtract A squared and B squared on both sides. So I end up with C squared, take away A squared, and take away B squared. And I'm going to be left with just the negative 2AB cos C. Now I can divide negative 2AB on both sides. Well, flip it and then divide by negative 2AB on both sides. And now I have an expression for the cosine of my unknown angle C. So this is actually cosine law, but just rearranged for angles. This is cosine law for angles. And we can now replace our lengths. Now, we got to be careful here. So 29 is C, right? That's opposite. 19 is A, and 16 is B, right? Because that's how we label these things. So we got to be careful when we substitute in that we substitute the right numbers. So let's see. 29 goes first. Oh, my box got too big there. So 29 goes first because that was C. So 29 squared, take away 19 squared and 16 squared, divided by negative 2 times 19, 16. And again, when we calculate these, take your time. Don't just plug it all in your calculator. Let's calculate the numerator and the denominator separately. So notice here that we're going to end up with a negative value for cos of C, which means that my angle is actually going to end up larger than 90, which makes sense. See, it's an obtuse triangle. It's not an acute triangle, right? So it's going to be 224 divided by negative 608. So be careful with the negatives, right? We don't lose track of those negatives. And we're going to have a negative value for cos of C. And again, solving for C, we just take the inverse of the cos, and we end up with 112 as our final answer. Okay, so I've been talking for about half an hour. That's quite a bit. I've done a whole bunch of examples here using sine law and cosine law. Okay, so just keep in mind, if you don't have a right angle triangle, you cannot use the primary trig ratios, and we have to use sine law or cosine law. And at any time, try to use the sine law. There's less operations, less places to make mistakes. Use that first. And then if you have situations where, so always use sine law unless, only times we use cosine law is when we have a contained angle or we have three sides. Okay, if we have no right angles and we have either a contained angle or we have three sides, like here we have 16, 19, and 29, we have to use the cosine law. Or remember, contained angle means I know this side, and I know the angle. So all the stuff is all together on around one vertex. Then we have to use our cosine law. Otherwise, please use sine law. It's much easier, less mistakes. Okay, so that's everything for trigonometry. Only needed 2 lessons here to get through all of it. We have our primary trig ratios, SOHCAHTOA, and we have our sine law and cosine law. All right, so try the problems in assignment 16, and best of luck. All right, so it's been a fun course. It's been fun making all these videos, and hopefully we'll have other courses together at some point. All right, so signing off for the last time. I'll be seeing you.